Whole numbers are 1, 2, 3, and so on. They're the answer to questions like how many, how much, which one of these. Actually, the answer to which one would be the third or the seventh rather than 3 or 7. That's an important technical difference and needs to be taught separately. They're ordinal numbers rather than cardinal numbers. But for the moment, in this course, we're really just interested in cardinal numbers. But while we're talking philosophy, notice also that number itself is an abstract concept. The thing we write on paper is not a number, but a numeral. It's a symbol that represents a particular number. The symbol itself is quite arbitrary, and I'll show you some alternatives in a minute. We use the Arabic base 10 system. For example, for the number 13, we use the Arabic digits 1 and 3, written in that order. But we can combine the same digits in a different way to get a very different number. For example, 113 is written by combining 2 1s and a 3. The meaning of the digit 1 changes depending on where we write it. The first one means 100, the second one means 10, and the 3 just means 3 in this case. But it could also mean 30, 3,000, or even 300ths, depending on where it's written within the numeral. This is exactly the same as in normal written languages. The digits are our letters, the numeral is the word, and the number is the meaning of the numeral. But there are a whole lot of other possible ways to represent whole numbers. The simplest is just to hold up your hand and start counting on your fingers. The word digit is actually a Latin word meaning finger or toe. You can represent numbers by a collection of objects. That's usually the first context you learn to count with. Gradually, real objects are replaced with counters or something else arbitrary to represent them. Then tallies and number lines, then written symbols, building abstraction layer by layer until eventually you get to algebra, where a single symbol can denote a whole range of possible numbers. But the written symbols don't have to be our Arabic digits. Here are some tiles from my Mahjong set. The blue symbols at the top of each tile are the Chinese representation of the green Arabic digits in the top left corner. Essentially, there are different graphical representation of those whole numbers. In fact, if you look at the first row, you'll see that the numbers 1 to 3 are drawn using digits that are just horizontal lines. The symbolic representation is arbitrary. These are just different ways of representing the same number. As a teacher, also look for ways to represent numbers using different positions. Get your students up and moving around and actively engaged in building physical and volitional representations of numbers. Make them gather in groups of particular sizes. Stand in a position that represents the relative size of a number. Step forwards and backwards along a physical number line to represent adding and subtracting. There are also many good ICT tools around for representing and manipulating whole numbers. These are especially good if you have a decent interactive whiteboard in your classroom. Okay, so here's a few hard questions about whole numbers. What's the first whole number? You might be surprised to find out that people disagree on this. If we're counting how many of something there are, then obviously the first number is 1. But if you want to say that you don't have any yet, well, then you need 0. Most mathematicians would say that the first and smallest whole number is 1. 0 isn't a whole number because you don't actually have a whole of anything. And indeed, the ancient Romans didn't even have a way to represent 0 in their number system. Okay, so what's the biggest whole number? How many whole numbers are there? Ask a child and you'll get any of a wide range of possible answers, depending on their age and level of education. Usually a nice round number or one either side. But the simple reply to that is just to add 1 to whatever they say. And of course that gives us the real answer to this question. There isn't a biggest whole number. Now you might try to say infinity, but be careful. Infinity isn't really a whole number. How can you have an infinite number of real objects? You'll always have a particular finite number of them. It might be large, but it'll still be a finite number. Infinity itself is a very tricky concept, and it doesn't follow the rules of normal numbers. I spent a whole semester studying infinity at university, and trust me, it's a very strange number. So the best answer to what's the biggest whole number is really just that there isn't one. Whatever big number you find, I can give you one that's bigger than it. Okay, so how do you compare whole numbers? How can you put them in order from smallest to largest? The simplest way is just to make a number line. Starting at 1, or 0 if you're a person who believes 0 is a whole number, lay out the numbers in the relevant position. By convention, we put the smaller numbers on the left and the larger numbers on the right. Or if you're going vertically, put the smaller numbers on the floor and the larger numbers up towards the ceiling. I mean, the direction is essentially arbitrary. It doesn't matter. But we want to reinforce some simple conventions to make it easier for our students to work reliably and systematically. And we read from left to right, so why not count in that direction too? And later on, when they get to coordinates on graphs and gradients leading to algebra, the same conventions they've used for many years can support and guide them as they explore new ideas.